Now, let us define what is a heat engine and what is a refrigerator. So, a heat engine is the normal engine which we talk in our common language: internal combustion engine, external combustion engine, petrol engine, diesel engine. These are all heat engines. So, in a heat engine, we give heat Q as input and we get work as output. So we give heat as input and we get work as output. Now, and in a refrigerator, we give work as an input and we take heat as output. Thus the refrigerator is the inverse of an engine. So now we will use a schematic diagram to tell the energy transactions, energy conversions in a engine. So in an engine there is a source of heat, that is suppose internal combustion engine, we say the petrol burned provides energy. So that is the source at some temperature T1 and it supplies energy Q1, heat Q1, and you see this some of the energy is rejected in the sink, that is at a lower temperature called T2, and this energy suppose radiated is Q2, that is went to sink, then the difference is converted in the work. So what is an engine? It takes Q1 amount of energy from the source, rejects some of the heat to the sink, and remaining energy is converted into useful work. So here this is work is output and this is input. So this is the schematic diagram of a engine, whereas this is the schematic diagram of an engine, heat engine. We call it heat engine. Now let us see refrigerator. So again, in a refrigerator there is source, correct terminology won't be source and sink. I will use something different here because, so this is cold reservoir and this is hot reservoir. So cold reservoir is the food stuff in a refrigerator which has to be made further cool. So what it takes some energy Q2 and rejects it to the hot reservoir Q1. So in order to do this, it takes work from the outside. So with the help of work from outside, that is the electrical power it uses, it takes heat from the cold reservoir and sends to the hot reservoir. So this is the opposite work of that is. So here work is input, and so Q2, the amount of energy it takes from the cold reservoir is the output, This is the output. So this is input, this is output. So these are the schematic diagram in which we describe a heat engine and a refrigerator. Now we are often interested in the efficiency of our machines, efficiency of an engine. We don't define for a refrigerator efficiency, but another term called coefficient of performance. let us see how we define efficiency and coefficient of performance, that is COP of a refrigerator. Now let us see how to define the thermal efficiency of a heat engine. So thermal efficiency of a heat engine is the ratio of work done by it to the heat absorbed from the source or hot reservoir. So you see here, so according to the schematic diagram, let us draw a short diagram. So this is source at a higher temperature, I say T1, it takes Q1 amount of heat and then it rejects some of the heat Q2 to the sink at a lower temperature, say T2, and then does some useful work. So we define thermal efficiency eta as work output by heat input. So the general rule of defining efficiency is, here work output means what we get, what is the final output, and here we will put those things for which we should pay the bill. How much money we are expending is heat input. So here work output, work by heat input Q1. Now according to the first law of thermodynamics, this work will be equal to the difference of these two, that is the energy we have taken and how much energy we have lost. So it is Q1 minus Q2 by Q2. So this is the expression for the thermal efficiency of a heat engine. The thermal efficiency eta can never be greater than 1. So it is always less than 100%. We can't have a 100% efficient engine. So this is how we define the thermal efficiency. So now let us learn about coefficient of performance for a refrigerator. So coefficient of performance for a refrigerator. So we call this COP. In short, we denote it by C. So we define COP of a refrigerator as the ratio of the heat removed from the cold reservoir to the work input to the system. So let us draw the schematic diagram of a refrigerator. This is a hot reservoir and this is a cold reservoir. So we have to extract heat Q2 from the cold reservoir and we have to give it to the hot reservoir, and for this we require an assistance from outside, that is the work. So this work is the input and Q2 is the output, what we get and what we pay. So we define COP as what we are getting is Q2 by what we are giving input as W. So we can write this as, so Q2, so this is only Q2 by W. We can write W in terms of Q2 and Q1 if we know, but generally we don't know Q1. We know how much what is the output and what is the input. So better to write in terms of Q2 and W only. This is how we define the COP. Now COP of a refrigerator can be more than 100%. So like efficiency, which is always less than 100%, COP can be greater than 100%. So this is how COP of a refrigerator is defined. Now let us take an example to see how to calculate the efficiency in a thermodynamic cycle. So a certain quantity of gas makes the cycle shown in the figure. The thermodynamic efficiency of the cycle is 1 by 12. Can this gas be radon? So here in PV diagram, it is shown this cycle 1 to 2, 2 to 3 and 3 to 1. This is the thermodynamic cycle, and the efficiency of the thermodynamic cycle is 1 by 12. So what type of gas could be the working gas in the system will be? So radon is monoatomic gas, ideal gas from monoatomic gas. So we have to find the nature of the gas as the working element. So when it is given efficiency, that means we have to analyze each and every sub process. So consider the path 1 to 2. So this is our path 1 to 2. Now during 1 to 2 path, let us apply this first law. Applying first law, delta Q is equal to delta U plus delta W. Now you see here, from 1 to 2, the volume is expanding. That means the system is doing work. As well as temperature is increasing. The isotherms are like this. So temperature is increasing. So temperature is increasing and the gas is doing work. This can happen only when some amount of heat enters. Suppose I say it is Q1. So Q1 heat enters into the system and there is a change in internal energy and there is a work done. What is the change in internal energy? That is number of moles N, this CV we don't know, into dt plus work done. Now let us see, from 1 to 2, the work done will be area under this trapezium. That is from here up to this trapezium. That will be equal to half into sum of the parallel side, that is P naught plus 2 P naught into that this 1 to 3, that is V naught, 2 V naught minus V naught, that is V naught. So we have Q1 is equal to NCV dt. Now this is, let it be dt only, plus this is 2 P naught, 3 P naught. So 3 P naught V naught by 2. This is equation number 1. So I got Q1 as NCV dt. Now suppose, let us further simplify it. Now I assume that this gas has a degree of freedom F. So I will write this Q as NCV is equal to FR by 2 dt plus 3 P naught V naught by 2. That is, I got Q1. This NR dt is P2 V2 minus P1 V1. That is F by 2 P2 V2. Here P2 V2 is 4 P naught V naught, 4 P naught V naught minus here P1 V1 is P naught V naught plus 3 P naught V naught by 2. So that Q1 becomes, this is 3 P naught V naught by 2, here 3 P naught V naught by 2. So we get F plus 1 into 3 P naught V naught by 2. This is what Q is. So this is for process 1 to 2. Now analyze process 2. Consider the process 2 to 3. 2 to 3. We have again first law, delta Q is equal to delta U plus delta W. Now 2 to 3, the process is isochoric, no work done. So this quantity is 0. So this quantity is 0. Next, the temperature here falls, no work done. That means temperature falls means the system is rejecting heat. So some heat is going outside. So if some heat is going outside, then we need not pay for the heat lost. So when we are using an engine, we only pay for the petrol purchase, not for the heat rejected, burnt out gases. So heat, here we are taking the heat, but here heat goes. So we need not bother about heat goes. Thus the system rejects heat to the sink. So in this process, the energy goes out. So we need not pay for whatever is going out. We should pay only for whatever we are using it. So next, consider the process 3 to 1. So now from 3 to back to 1. So again, delta Q is equal to delta U plus delta W. Now delta Q is equal to delta U, which is here. Now as the temperature it is decreasing and work is done on the gas. You see, the volume of the gas is decreasing. That means we are doing work on the gas. So we are compressing a gas, we are doing work on the gas, and its temperature is decreasing. Its temperature was previously 70 degree, now it is 60, 50, 40, 30 like that. That can only be possible if again it rejects heat. So thus we see that the system rejects heat during 3 to 1 also. 3 to 1 also. Like 2 to 3, 3 to 1 also the system is rejecting heat. So what we have got till now is that total energy is absorbed during this process 1 to 2, and this energy is this much. So this is the conclusion till now. Now in this thermodynamic process we have calculated the heat absorbed. Now what is the output we are getting? The output is in the form of work. So now let us calculate what is the work output. So now let us come to the work output. Work output of the cycle is equal to area under the PV cycle. So that is work done will be equal to half times that base, that is V0, 2V0 minus V0 into altitude, that is 2P0 minus P0, that is P0 V0 by 2. Now it is given in the problem that the thermal efficiency of the cycle is equal to 1 by 12, that is defined as work done by heat input. So we have 1 by 12 as work done is P0 V0 by 2, and the heat input given is F plus 1 into 3 P0 V0 by 2. So we have 3 P naught V naught by 2, this cancels. So here 3 and 4 here gets cancelled. So 4 is equal to 1 plus F implies F is equal to 3. Thus the working substance must be an inert gas, i.e. with 3 degrees of freedom. So inert gas or monoatomic gas. Inert gas because it was given as radon, so inert gas or a monoatomic gas. So monoatomic gas means inert gas.